Okay, so what we will do now is we will try and see the physical code which implements the localization without GPS. You have seen the bicycle, we have seen where the sensors were placed, what were the sensors that were used and all that. So just now let us summarize and look at the code. But before you start looking at the code, it is important to understand the philosophy of trying to localize this cycle, right. You are trying to so that you have to get very clear. Look at it this way, as you are driving the bicycle, often at very low speed you hold the handle, because of at low speed you are unstable. So the handle keeps shifting all the time, right. So sometimes when you apply brake or your front wheel shifts, or your when you are moving very slowly, the front wheel sort of not wobbles but sort of moves around, perhaps not in a straight line, keeps moving a little bit. All this means that look at what the sensor is going to see. Sensor all the time, look at magnetometer, okay. So the magnetometer will give you lot of fluctuating values which often mean nothing. You are not changed any direction, but magnetometer is reflecting all that. So somehow you have to keep in mind that okay, so there can be lot of values from magnetometer, but I must have an algorithm, my own algorithm, which will sort of eliminate all those values and sort of ensure that there is no change in direction. You will not have that much of a problem with Hall sensor. A pulse will come only when there is a wheel rotation, okay, that is okay. So now you can say you can actually start thinking about your algorithm. If there are no pulses, coming, but the magnetometer continues to indicate values, clearly someone is playing the fool with the handle, right. He is just moving up and down and then creating a lot of data from the magnetometer, which is not going to it is not going to help you. You can also have a situation where pulses are coming very slowly, but there is a lot of fluctuation in the magnetometer, which is clearly an indication that you are at low speed. And you may end up with a situation where large deflections can come and you are not even sure whether you have actually done a 90-degree right turn, or whether you have done a 90-degree left turn, you have turned left, you have turned right and so on. So all of this means your algorithm should be robust enough to take care of practical situations of problems of this nature. The code that is written and the code that I would like to share with you is just a overview which will work, okay. But several modifications to this code is up to you. You may want to try and you may want to modify based on your local settings. This is one part of the story. The second part of the story is, we mentioned that you will start with one assumption, that you have the last well known GPS coordinate, right, and soon after you will start losing GPS. Quickly you will absorb that last lat long and you will ask your algorithm, which is called the localization without GPS algorithm, to kick in and say, hey, I have the last GPS coordinate, do something with it quickly. What is this quickly? You have to take this last GPS coordinate and pass it through that UTM routine which I mentioned to you, right. So you pass it through that, you will end up with some XY. Essentially GPS will give you all the latitude and longitude and other height and other related information, which often may not be useful, because in the localization paradigm that we are talking here, we are purely looking at 2D from wherever we have lost to some reasonable distance where other parameters given by GPS may not change significantly, okay. So that is the assumption. So then you get back, you convert this latitude and longitude to some realistic x and y, keep it with you and say, hey, this is the last xy I know for sure where I am from the GPS. Of course the map is there with you, the map definitely you have to, that is your reference, which you have with you. It can be offline also, it is a map that is just stored on your computer and which you want to keep mapping back, right, because you do not have GPS now, somehow you have to map it back and say where am I, if you want to ask, this is the final application, right, where am I, if you want to know, you have to consult the map only, that is the only way that you are going to use this application. So somehow you have to hold on to that original I would say x and y coordinates and keep updating this coordinate as and when you get this magnetometer information coupled with the Hall sensor information. Hall sensor is perfectly going to tell you that you have done a rotation, right, that means linear motion has been converted to some circular motion has been converted to some linear distance, and that is when you get a pulse, and then you know the circumference, and from there you find out linear distance and all that you can do, simple geometry stuff, and then you will arrive at some linear distance. Be careful, magnetometer is going to be very noisy, and as I told you the handle shaking can give you a lot of data. So you need to do proper thresholding, and once you do that, you know, yes, I have taken a left turn, I have taken a right turn, or I have done nothing, I am proceeding straight, and so on and so forth. Then take that xy, and now if you ask yourself where am I, you what should you do, you have this xy with you which you got from all this wheel rotations and all that. Take this xy, you have the original xy which you got from the UTM conversion of lat long, latitude and longitude, add it back to that, add it like an offset back to it, and then put it back on the map, then you know exactly where you are. So this is the core idea that you have to follow if you want to do all of this. Let us see whether this code that we were talking of actually does all what I said as in a summary. Let me point you, before showing you C code, let me just point you to what all you should look for in the C code, because it is going to just give you some C code, some variables and some for loops and so on, which is perhaps of not much consequence when we at the moment. So you must get the high level picture of what is happening. So let me point you to this. Here is the algorithm of interest, that is what we want to do. First step is, as I said, get hold of the lat long of the last GPS coordinate, and I have marked here that lat long is required for all Google Maps. If you want to put back anything into Google Map, you will have to do it with latitude and longitude, and therefore you will have to get hold of conversion, which we will come to later. So you have the last latitude longitude, step number 1, store it safely and pass it through UTM and store the original xy carefully somewhere. Next step, sensor output. What are the two sensors? You have the Hall effect sensor and you have the magnetometer sensor. Two variables you will find in the C code. One is called the distance array essentially, and then the magnetometer theta array, right. Essentially the third step will be all what I discussed a few minutes ago, the zeros from distance will have to be removed as well. Sometimes even the Hall effect sensor will give you some kind of numbers which are quite vague, not just filtering with respect to magnetometer, but also you have to remove the zeros coming from the Hall effect. You will find, actually when you do that, you will find that you will get some zero values which do not actually make any sense. It should give you some number. Of course that number will depend on what is the circumference of the cycle and how often it repeats that, and some sort of a cumulative count which will have to come because of the wheel rotation. So I have shown you a cycle wheel, and every time a one rotation happens you get a pulse. So you start putting it into this distance array, you count that, and then you put the next count, which will be the first count plus the next count, that is after 2 rotations, then third one will be the first, second and third, and so on and so forth. You go on this way, you start cumulatively counting and you actually come to the linear distance, that is the key objective, right. I have written, you must know the radius of the wheel, and therefore I expect you to do this calculation and then find out the linear distance. Now look at the magnetometer. We mentioned to you already that it is with respect to earth's magnetic north, that it gives you a number which is also in some degrees, right. So you will see that 45 degree means essentially the vehicle or bicycle is moving in the northeast direction and so on and so forth. Okay. Actually before you do any of that cleaning up process, you have to do this fourth one, which is where am I you want to know, right. So magnetometer is going to tell you something about where you are with respect to the existing sensor based system. So you again rely on the magnetometer, you know where you have lost the GPS, exactly there what was the magnetometer reading you take. Supposing it read a value which is 180, in the experiment that you do it can be anything, it can give you 270, some value it will give you, take that as 0, then you start convert everything to positive values, because negative does not make sense, you will see that in code, and use that starting magnetometer value which you made it as 0, use this 180 degree as an offset and start subtracting this offset from the starting point. So somehow your magnetometer is keeping track of the direction essentially. So this is when you say reference, your magnetometer is now calibrated with respect to the GPS, and the particular direction in which you are proceeding. So you are starting by saying everything is 0 now, and from here I will start tracking the magnetometer accordingly, that is what you are saying in step number 4. Now come to step number 5, left turn, right about turn, all these are very good possibilities, right. Again you have to be dependent on the magnetometer to get to know where you have actually turned. I told you about that problem, you can be just moving your handle and creating a situation where the magnetometer is giving you out values after you have done this 0, okay, after you have done this 0 calibration it is giving you some values, it is not going to make sense if you are not getting pulses, which means all those have to be discarded. So this decision making process is a very important thing. Here you have to do some kind of thresholding. In the example that I am going to show you, theta r is between 45 degrees and 135 degrees. Then you say you have done a 90 degree turn. If it is between 225 degrees and 315 degrees, I am saying I have done a left turn, right. Actually you do the experiment, you do a right turn, do this 0 calibration, and then you turn and see what actually happens and put those values into your code, right. Also this 180, in my case it is 180, when you started with the last known GPS value and you want your magnetometer to keep track of the direction, it may be something else, it may be 40, it may be 30, it may be 20, whatever, that you make it 0 and then you start from there, that is the point of doing this referencing part. Now you are getting an array of magnetometer values, right. So you have to repeat for all values of theta r that you collected, except that the second value of the array of magnetometer values that you have will have to be with respect to the first one. So you take a difference of the first one. The third value in the array will be a difference with respect to the second one, the fourth one will be with respect to the third one, and so on and so forth. And therefore because you have to keep track dynamically, right. So the first one you put this thresholding, and then this thresholding anyway is what you are trying to say about your turns and all that, and then remaining parts you will have to keep doing this by taking the difference of the second with the first and then applying this rule back. You apply this rule back after you take the difference for second values onward, from the second value onwards, and then you will definitely arrive at some reasonable xy position. So then what do you do after that? What you do after that is pretty straightforward. Remember, your last known GPS coordinate was the latitude longitude. you have now passed it through this UTM, then you got the original xy, the original xy I meant the last known xy as with respect to GPS, and then you did all this wheel rotations with dist array and theta array, you found out what is the linear distance and all that, and then you arrived at the new xy, right. The new xy again will have to pass through this UTM, and then you will have to get back to the GPS coordinates on the map, right. So that is the key takeaway. So this point, when you do this step, that is get the new xy and put it back into, pass it through the UTM routine and get back the GPS coordinates, will actually say, is actually this final step where a human wants to ask the question, where am I? When you ask this question, this will have to happen, this conversion will have to happen, and it will nicely show you on a Google map the position, the current position even without GPS. So that is the nice thing about this little application. So let us now run through the code. I will show you some C code, but I will not spend too much time because I have mentioned to you all what you should be seeing. Let us point out to some important things with respect to this understanding that we have. So let us say I have to now show you the last GPS latitude and longitude. Look at the point where Nitesh Nayak is actually pointing on the screen. There you see that is the last initial latitude and longitude that you have, right. So store this somehow. You have seen that the two variables are mentioned, lat underscore init and long underscore init, super. Now let us go to step 2, which is the sensor output. There are two variables, distance array and theta array. One is the Hall effect sensor and the other is the magnetometer systems. Look at the Hall effect which is essentially the distance array. So let us just highlight that. Look very carefully, there are no zeros there, okay, which means Nitesh Nayak has actually run through some algorithm to get rid of all the zeros in that array. In practice it will not be so beautiful, you will see a lot of zeros. So you have to design your own algorithm to get rid of the zeros and put it there, okay. So that is distance array. Look at theta array. In theta array is the second one, which is telling you the magnetometer values. Here it is telling you different degrees, 272.45, 261.74 and so on. So it is actually giving you all the magnetometer values. Now look at the filtering, removal of zeros I already mentioned to you, do not worry about it. Let us look at the next filtering step, which is the magnetometer should be made 0. The magnetometer should be made 0 at the point when you have your last GPS coordinate, okay. I mentioned to you at the point when I lost the GPS, the magnetometer read 180 degrees, right. Now you see what is shown here, var temp is equal to theta array I minus 180 degrees. In your case it can be something else. Essentially if you do that, you are making your system back to 0, everything is nicely done, and then you convert into all positive values, all that you can see that temp plus 1 360 and all that is shown here. So it is essentially converting everything to positive values. Now is the issue of decision making, lot of noise coming from the magnetometer. Do it very carefully, set your own thresholds, left turn, right about turn and all that will have to be taken care, because you are cycling and then you are moving forward. So there can be left turns and right turns. Threshold setting is important. Look at theta array, it should lie between 45 degree and 135 degrees to tell you that it is a right turn of 90 degree right turn, okay. So that is where it is getting pointed to. There you see it is exactly there. Those ones that are being highlighted will tell you some idea about right turn. Now let us look at left turn. Theta array should be between 225 degrees and 315 degrees. There you are 315, yes, that is 315 and 225 degrees, fantastic, that is a left turn. That is going to tell you that decision. So again this decision making is what we have found for the terrain that we were trying to sort of map, trying to find the location without GPS, but you will have to try on your own for your own terrain and for your own localization application. This is completely open source, you should be able to download without breaking your head too much. You should be able to essentially get hold of the xy coordinates from the last GPS coordinate that you have, which is essentially the xy coordinate. Let us go and look at that. First GPS, last known GPS to the first xy. Okay, so there you are, right, which is essentially showing you the last xy, last known good xy. So then there is the next is the new xy which we have to convert back into GPS. Where is that part? Can we go to that section? Right, map lat long to xy, right. One is the first part, that is you take the map coordinates, latitude and longitude and convert it to xy, that is this part. This part is done here in this part. Now you can also do map xy to lat long, that is this path, this part is done here. So you can see both the routines are shown, and I encourage you to look at the this application, and then you will be able to essentially localize quite accurately provided you do all these steps which I broadly discussed. So in summary, you need those nice little what shall I say, pin up board markers, right. So essentially those pins that we use on a sort of a pin up board. So you might have seen that equivalent in electronic form on Google Maps, right. So that is this function that you see here is the updated marker function, which will just take the converted lat long from this UTM application where you converted xy to lat long, and then call this function updated marker with a simple Google API call. You should be able to put back that pin on the map. That is what we saw in the slides as well. You saw a set of pins on the as the path was being traced, you saw a set of pins, and those pins essentially are from this part of the function call. So hopefully you can try this and then improve on this existing code which will be made in open source, and be in touch with us with respect to your own attempts in trying to do localization without GPS.